Okay, I'm going to walk through the first of the eigenvector problems by hand, and then I'm going to walk through the next several using MATLAB, and then we'll go on from there. So the first eigenvector, the first matrix that we want to find the eigenvectors and eigenvalues for is 2, 1, 0, 3. So we make this characteristic expression of lambda I minus a, which means we take lambda minus 2 here. 0 minus 1 is going to be negative 1 there. 0 minus 0 is 0. And lambda minus 3 here. And then we want to take the determinant of that. So it's a 2 by 2, so you go down, which is going to give me lambda minus 2 times lambda minus 3 plus 0. So this is the same as lambda minus 2 times lambda minus 3. That's equal to 0, meaning that lambda is either 2 or 3. Now, I think I made lambda 1 equal to 3. And if you look at what happens, if you take 3i minus a, you get 1, negative 1, 0, 0. We want to throw that into Gauss-Jordan, which doesn't do anything. When you put that through Gauss-Jordan, you're going to get 1, negative 1, 0, 0 back. So literally what we're being told here is that x1 minus x2 is 0, determines all of the eigenvectors. So if we let x2 equal t, that means x1 has to be t, which means that t times 1, 1 gets me the set of all eigenvectors that correspond to the eigenvalue 3. So now we need the eigenvectors that correspond to the eigenvalue 2. So if we take 2i minus a, we end up with, well, let's see, 2 minus 2 is 0, right? 0 minus, so this is still going to be negative 1. We put a 0 here. 2 minus 3 is negative 1. So this is the matrix we get. We threw that through the Gauss-Jordan game. And we're left with 0, 1, 0, 0. So what we do know in this is that x sub 2 has to equal 0. X sub 1 can equal anything. So if we multiply t times 1, 0, that should give us all the linear combinations that this can be. So these are all the possible eigenvectors that correspond to the eigenvalue 2. So MATLAB speeds up this process. It doesn't give us nice, neat integer answers, but it does give us correct answers for the eigenvectors. So let's take a look at how that works. Alright, so in the next problem, number 2, our matrix is 1, negative 4, negative 2, 8. We use the overload for the function, so I'm going to use VD as a matrix there. Is going to be the eigenvalues and eigenvectors of A. And if I think I have something wrong here. Nope, I have this correct. I have to clean this up in the answer sheet that I put. I'll fix that. What you're told here is that you have 2 eigenvalues. They're going to be the ones in the diagonal there. So 0 is one eigenvalue, and the other eigenvalue is 9. So you have a full set of eigenvalues here. and you also have a full set of 2 eigenvectors. So the eigenvector that corresponds, or a set of eigenvectors that correspond to 0 is the first column of V. So that's going to be some parameter t times the vector negative 0.9701 and negative 0.2425. The second set of eigenvectors, the one that corresponds to the eigenvalue 9, is going to be 0.4472 and negative 0.8944. Alright, so there we go. Alright, so let's look at number 3. The given matrix there is going to be 201, 034, 001. So we use that same command VD of eiga. It has 3 eigenvalues, 2, 3, and 1. So the ones that correspond to 2 are going to be t times 100. The ones that correspond to 3 are going to be 010. And then this last column are going to be the eigenvectors that correspond to 1. Just so you see what's going on here, the results that you're getting here are actually going to be eigenvectors with the they're unit eigenvectors. They're the eigenvectors with the magnitude of 1. Okay, so that's why you're getting these kind of funny answers. All right, so let's look at number 4. The matrix that I get for 4 there is 1, 2, negative 2, negative 2, 5, negative 2, negative 6, 6, negative 3. So I run the routine on this, and you're going to see in this problem, you actually get a doubling there for the eigenvalue of 3. So the eigenvalues that are available are 3 and negative 3, but there's 2 sets of eigenvectors that go with 3 here. So the first and third column of V are going to be sets of eigenvectors that go with 3. The middle column of V is a set of eigenvectors that go with negative 3. All right, so let's take a look at 5. So you have A is 1, negative 2, 1, 0, 1, 4, 0, 0, 2. Now this one's pretty easy to see what the eigenvalues are because they're going to be the 1, 1, and 2 going down the diagonal there. All right, so let's run that eiga. And again, like I said, you get that 1, 1, 2 going down the diagonal because it's an upper triangular matrix. And you're going to get, see now this one, you have 1 showing up twice, but it's the same set of eigenvectors. So you only get 1 eigenpair there. And then for number 2, you're going to get that last eigenvector set along the way. Okay, so 6 is one that's 4 by 4. It's 1, 0, negative 1, 1, 0, 1, 0, 1, negative 2, 0, 2, negative 2, 0, 2, 0, 2. Okay, so there's my matrix. I run the routine on this, and it tells me that I have 2 eigenvalues. I have the eigenvalue 0, and I have the eigenvalue 3. And the zeros both correspond to, and that's going to be a negative root 2 over 2 for both of those. And the 3's correspond to the same 0.4472 and negative 0.8944 in the first and third spots. So there you go. We're going to tuck away MATLAB for a minute here. We're going to look at a few proofs, and then we'll move on. So the first one says, how do I know that lambda is 0 if and only if A is non-invertible? So this is an if and only if. We got to go both ways on this. So let lambda be 0, okay? And an eigenvalue for A. All right, so this is going to imply that 0 times lambda minus A determinant has to be 0. Well, 0 times lambda, or 0 times I, sorry, times A minus A has to be 0. Well, 0 times I is just 0, so this is going to imply that the determinant of negative A is 0, which means that the determinant of matrix A is 0, which means that A is singular. And you can literally just go backwards to get the if and only if here. So that is a proof for number 7. All right, problem number 8 says, how do I know that A and its inverse have the same eigenvectors? So let X is an eigenvector of A. This means that AX has to equal some lambda X, right? So take the inverse of both sides. Which means that X is now lambda times A inverse X, which means that A inverse X has to equal 1 over lambda X. So this is a constant times X, so this is going to tell me that X is an eigenvector of A inverse, and you can play this game backwards to show that everything that's an eigenvector of A inverse is also an eigenvector of A. So this is number 8. Number 9 just asks the question, what's the relationship between the eigenvalues? Well, if lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of A inverse. That's like in this problem number 8. So it directly follows. The conclusions you need for number 9 are directly following from the work in number 8. Let's do number 10. Okay, so number 10, we want to prove that A and A transpose have the same eigenvalues. So we want to prove that A and A transpose have the same eigenvalues. So we want to start by saying, let lambda be an eigenvalue of A. Well, this tells me, so let's consider the matrix lambda I minus A transpose, and note that that's going to be equal to lambda I minus A transpose, because the transpose of a sum is the sum of the transposes. If you transpose the identity, you get the identity back, so these two have to be equal. Think about that for a minute. This means that the determinants have to be the same. If lambda is a sorry, let's not go there yet. If the determinants are the same, the determinant of a transpose is equal to the determinant of the matrix. So that kind of works like this. Oops. At this point you have it, because this has to be 0 if lambda is a eigenvalue, which means that this also has to be 0, which means that lambda is an eigenvalue of A transpose. So A and A transpose have to have the same eigenvalues. You can work this the other way, just start with A transpose and you're going to end up in the same place. So that makes it work both ways. So there you have it. That's the solutions to the eigenproblems. If you have questions, drop me an email, show up in the drop-in, and I'll see if I can clear up some things. All right, thank you.